In problem 3, we'll be talking about the bias variance decomposition. And so in this question, it says, let theta hat be a point estimator of the true parameter theta. The variance, bias, and mean squared error, the MSE, of theta hat are defined here. And now, based on these equations, it wants us to show that the mean squared error of this point estimator is equal to the variance of it plus the bias squared. Now, before we dive into this question, I want to do some quick clarifications on values and notation. And so when we talk about a point estimator, I think it's pretty important you conceptually understand what a point estimator is. So this point estimator is essentially trying to estimate the true theta, right? But how do we estimate the true theta? This theta hat, it actually depends on random data. And so another way to think about it is every time you have a data set, right? So every time you have a data set, theta hat actually changes across random samplings. And so let's say I want to try to find the true mean of a bunch of numbers in a hat. And so how I do that is I don't know what the true theta is, but instead I just draw a random number, like a random fixed number of like paper numbers from my hat. And I'm like, oh, what are these numbers? And I find the mean of those numbers, and that gives me one theta hat, one estimate. And I can do this multiple times and get many, many estimates. And then after many of those estimates, now we can start seeing what is the variance of all of these estimates, what is the bias of all these estimates, and what is the mean squared error and the expectation and such. Okay, so now that we've clarified the difference between a point estimator theta hat and the true parameter theta, which is just one value, like let's say the hat contains all these numbers and the mean is 5. Like no matter what, the true mean is always 5. The true parameter is always 5. And so this is a constant versus this is not. Okay, continuing on, now we have definitions of the variance, the bias, and the mean squared error. And so you can tell by this equation that the variance essentially tells us how much our estimate fluctuates, right, around its own average. So we can have a bunch of theta hats, and then we can have the expectation of the theta hat. So like after like doing this experiment a bunch of times, what is like the general, like what is the expectation of this parameter? And we subtract that from this current parameter estimate, and then we essentially kind of see like how is our data like spread, right? Every time we like draw a new data hat, like what is the spread of our data? And so this variance tells us how much estimate fluctuates around own average. Okay, and then we have the bias. And so notice how the bias is the expected value of our point estimate minus the true parameter. And so this tells us how basically the expected value of, or basically how far our estimate is from this true value, like how good or how bad our estimates in general actually are. And so the bias tells us how far the expected value of our point estimator is from true parameter theta. Okay, And lastly, we have the mean squared error right over here. And it's basically we take the error between like our estimate and the true parameter and we square it. And so this is literally just the expected square error. And what we want to show is that the mean square error can be represented as the variance of the point estimator plus the bias of the point estimator squared. Okay, and this entire thing is called the bias variance decomposition because we can decompose the mean squared error into the bias or the variance. Okay, and so let's solve this problem. Before we dive in, I'm going to remind you on some quick equations that you should have seen in CS70, and if not, it's fine. Here they are. And so the first one is the variance of some random variable x is defined as the expectation squared, like the x squared, expectation of that, minus the entire expectation squared. And that just comes from the definition of variance. Once you like simplify that, this is the equation. And lastly, the variance of some random variable plus a constant is just the variance itself. And this makes sense, right? Because shifting doesn't affect the spread of the data. So even adding a constant, it doesn't change the variance at all. Okay, now let's solve the actual question. And so we have that we're given that the MSE, the mean square error, is equivalent to this equation right over here. Okay. And notice how if we treat this entire thing as like an x, right? Then this is just e to the x squared. And from our formula here, we can basically say the variance, since the variance of x is equal to the expectation of x squared minus the expectation of x, all of this squared, then we can move this to the other side and have the property that e of x squared is equal to the variance of x plus the expectation of x squared. And so let's write this out. We can thus say that this mean squared error is equal to the variance of our x, which we define as theta hat minus theta, plus the expectation of theta hat minus theta, which is our x, and then we square this entire thing. Okay, and I'm going to start by simplifying the variance over here. And so what you will notice is, remember that our parameter is just a constant, right? It's literally just a constant. So you can think of this as essentially the variance of some random variable plus c or minus c, it doesn't matter. It's being shifted by a constant. And again, from our equation, we know that adding a constant to any random variable, it doesn't actually affect the spread of the data. Ooh, I don't know if you can see that. Yes. So the variance of like shifting the variance doesn't actually affect the variance at all. Okay, and so we can basically just remove this constant, right? This is our true parameter. It's literally just a constant. And so we can say this is equal to the variance of theta hat plus, and within our expectation, by linearity of expectation, we can split this into two expectations. This is equivalent to the expectation of theta hat minus the expectation of theta, and then we square this entire thing. And the expectation of the true parameter, well, the true parameter is just a constant. It's just a number, right? It's like in our hat with a bunch of numbers. It's the true mean of all these unknown numbers in my hat. And so the expectation of our true parameter of a constant is literally just theta. And now you'll see that this equation becomes the expectation of theta hat minus theta squared. And if you notice in our equations up here, the bias is actually defined as E of theta hat minus theta. And so see, E of theta hat minus theta, they're literally the same. And so this interior is literally just the bias. And so this whole thing right here is literally just the bias of theta hat squared. And so therefore our mean square error, we've just shown that it's equivalent to the variance of theta hat plus the bias of theta hat squared. Perfect. Let me just, let's actually highlight it to make it clear. So we've just shown that the mean squared error is equivalent to the variance plus the bias squared. No, okay, there we go. Okay, and so what are our takeaways? Well, our first takeaway is that the mean squared error, the error basically, it must come from either bias or variance. And that kind of basically sums up like our error. When we have an error, we can basically describe it as it's either because it's biased or the model is biased or because there is like variance. And besides that explaining the error, some other thing that's not completely related to this, so like it's not really due to this equation, but what's good to know is for simple models, like imagine like just a constant model where you're always predicting 5 all the time, right? The bias is very high, right? Because simple models don't necessarily catch the data as well, right? Like let's say we're trying to predict our mean from this hat with a bunch of numbers in it, and we just have our model be constant model. So we predict 5 every time. The mean is always 5, right? So it has really high bias because it's probably always wrong, low key. And the reason is because the simpler models, like let's say like constant models, y equals like 5, like it can't capture the data as well. But this simple models also have lower variance, right? If we're always predicting 5, our predictions are very, very like consistent, right? It's not jumping around, like it's not 10 one day and then 2 the other day, whatever. So our variance is really low. And so again, for simple models, our bias is high and our variance is low. Equivalently, for complex models, let's say we have this really, really, really complicated equation to represent like the mean, right? Our prediction. So our bias will be lower because we are essentially doing very well at capturing what our mean is because it's a complicated model. However, our variance might increase, right? Depending on the data. Because this model is like very complex, it's very prone to like outliers and stuff like that. Okay, and so that concludes here. Actually, let me just, no, it's so big. Let me just do this so anyone referencing the notes can see kind of the big takeaways. But yeah, that concludes problem 3, and we will see you in discussion 6.